Are you aware of how operating systems manage multiple tasks at once? This video explores the principles and challenges of concurrency in operating systems. Discover the intricacies of managing concurrent processes efficiently. Concurrency in operating systems refers to executing multiple processes simultaneously. It allows tasks to overlap in execution, improving CPU utilization and enabling efficient multitasking. This is particularly important in environments with multiple users or background processes. It enhances system performance and responsiveness. By allowing the OS to switch quickly between tasks, users experience faster feedback and smoother operation, even under heavy workloads. Real-time applications and interactive systems benefit significantly from concurrency. Processes are independent units, while threads share memory within a process. Each process has its own memory space, making them isolated and secure, whereas threads within the same process share the same address space, allowing faster communication but requiring careful coordination. Context switching allows multitasking even on single-core systems. The CPU saves the state of one task and loads the state of another, giving the illusion of parallelism. Though efficient, context switching incurs overhead and must be managed carefully to avoid performance loss. Synchronization is crucial to prevent data inconsistency among threads. Techniques such as mutexes, semaphores, and monitors ensure that only one thread accesses shared data at a time, preventing race conditions and ensuring reliable outcomes during concurrent execution. IPC enables data exchange between processes through various methods. Shared memory allows direct access, while message passing involves sending and receiving operations. Low-level IPC offers speed and control, but requires careful synchronization. High-level IPC abstracts complexities, enhancing ease of use. Both approaches have distinct advantages and challenges. Concurrency introduces complexities like race conditions and deadlocks. Race conditions occur when multiple threads or processes access shared data simultaneously, leading to unpredictable outcomes if not properly synchronized. Deadlocks arise when two or more processes are stuck waiting for each other's resources, causing the system to halt part of its operations. Live lock and starvation are other issues affecting performance. In a live lock, processes continuously change state in response to each other without making progress, while starvation happens when a process waits indefinitely for a resource because other higher priority processes are continuously favored. Priority inversion occurs when a low-priority process holds a resource needed by a high-priority process, preventing the latter from proceeding. This can lead to unexpected delays and system inefficiencies, especially in real-time systems if not handled with techniques like priority inheritance. Independent processes operate without affecting others, suitable for isolated tasks. Cooperating processes share data and interact for joint tasks. They rely on IPC mechanisms like shared memory and message passing. Independent processes are easier to design with fewer risks. Cooperating processes require synchronization to avoid errors. Concurrency involves multiple tasks progressing independently, not necessarily simultaneously. Parallelism requires simultaneous execution on multiple cores. Concurrency can work on single-core systems through context switching. Parallelism enhances performance by running tasks on different cores. Both concepts are crucial for efficient system operations. Concurrency improves CPU utilization by keeping it busy during I/O waits. While one process waits for input-output operations to complete, the CPU can execute another task, ensuring minimal idle time and maximizing throughput. It enhances responsiveness in user interfaces and real-time systems. By allowing background tasks to run independently from user-facing operations, concurrency ensures that applications remain smooth and interactive even under load. Modular program design is encouraged through threads or services. Threads within a process or microservices in distributed systems help developers break down complex tasks into manageable concurrent units, improving maintainability and flexibility. Concurrency forms the basis for parallelism in multi-core systems. While concurrency allows multiple tasks to be managed at once, parallelism takes this further by executing them truly simultaneously across multiple cores, boosting performance significantly. Scalability is achieved by efficiently managing multiple tasks. Well-designed concurrent systems can handle increased workloads gracefully by distributing tasks across resources, making them suitable for everything from desktop apps to large-scale cloud platforms. Shared memory allows multiple processes to access a common memory segment. It offers high speed as data is not copied between processes. Synchronization is necessary to prevent race conditions. This approach is efficient for large data exchanges. However, it requires careful management to avoid data corruption. It uses send and receive operations for data exchange. It is suitable for distributed systems and client-server models. Deadlocks occur when processes are stuck waiting for each other's resources. Key conditions include mutual exclusion and hold and wait. No preemption and circular wait also contribute to deadlocks. Detection involves identifying cycles in resource allocation graphs. Strategies include resource ordering and deadlock avoidance algorithms. Race conditions arise when the outcome depends on execution order. Multiple threads accessing shared data can lead to data corruption. Locks and mutexes enforce exclusive access to resources. Atomic operations and thread synchronization constructs help mitigate risks. Concurrency libraries provide built-in mechanisms to prevent race conditions. Designing for concurrency involves adopting thread-safe patterns. Limiting shared state reduces risks of data corruption. Higher-level abstractions like message passing avoid shared memory issues. Testing tools detect and debug concurrency problems. Continuous testing and disciplined design principles enhance reliability. Low-level IPC operates close to the hardware, offering speed and control. These mechanisms are typically implemented within the operating system kernel or through direct system calls, enabling fast and precise communication between processes. Shared memory and semaphores are examples of low-level mechanisms. Shared memory allows multiple processes to access a common memory region, while semaphores coordinate access to that region, ensuring synchronization and preventing conflicts. They provide fine-grained control over resource access. Developers can manage how and when processes interact with shared data, which is critical for maintaining consistency and avoiding race conditions in time-sensitive applications. Efficiency is achieved through direct memory access without context switching. Since processes communicate through memory rather than message passing, there's less overhead, resulting in faster data exchange and lower CPU usage. These mechanisms are foundational to system software. They underpin many core operating system services, including memory management, scheduling, and device communication, and are essential for building robust, high-performance applications. High-level IPC abstracts low-level complexities, simplifying development. Examples include remote procedure calls and sockets. It enhances interoperability across different machines and platforms. Built-in security and fault tolerance are often included. High-level IPC supports modern architectures like microservices. Low-level IPC offers high performance with less overhead. High-level IPC is user-friendly and language-agnostic. Scalability varies, with low-level IPC limited to single systems. High-level IPC supports distributed systems and networks. Security is minimal in low-level IPC but enhanced in high-level protocols. Resource ordering prevents circular waits, avoiding deadlocks. Deadlock detection uses wait for graphs to identify cycles. Recovery involves terminating or rolling back processes. Avoidance algorithms like Banker's algorithm pre-validate requests. Timeouts and retries help manage resource acquisition conflicts. Locks and mutexes enforce exclusive resource access to prevent race conditions. Atomic operations ensure thread-safe modifications. Synchronization constructs like semaphores control thread execution. Immutable data structures prevent modification after creation. Concurrency libraries offer tools to manage race conditions effectively. Concurrency design involves adopting thread-safe patterns like producer-consumer. Limiting shared state reduces synchronization needs. Higher-level abstractions like message passing avoid shared memory pitfalls. Testing tools help detect concurrency issues early. Continuous testing and disciplined design enhance application reliability. Low-level IPC is crucial for performance and resource control. It enables direct communication between processes with minimal overhead, making it ideal for time-critical and resource-constrained environments like embedded systems and operating system kernels. High-level IPC simplifies development and enhances interoperability. Mechanisms such as sockets, remote procedure calls, RPC, and message queues abstract the complexities of low-level interactions, making it easier to build distributed or networked applications across different platforms. The choice depends on system architecture and performance needs. Real-time or low-latency systems may favor low-level IPC, while application-level software and cross-platform services benefit from the flexibility and ease of high-level IPC. Both levels are often combined for balanced performance and usability. For instance, a system may use low-level IPC for internal process coordination and high-level methods for communicating with external services or user interfaces. Understanding their roles is key to robust system design. Selecting and integrating the right IPC mechanisms ensures efficiency, reliability, and scalability in both system software and modern application development. Concurrency challenges include managing resource conflicts and synchronization. Deadlocks and race conditions are common pitfalls. Effective design and testing are crucial for reliability. Understanding IPC methods aids in managing concurrent processes. Continuous learning and adaptation are essential for handling concurrency issues. In conclusion, concurrency in operating systems involves executing multiple tasks efficiently. It enables systems to maximize resource utilization and maintain responsiveness even under heavy workloads. Understanding concurrency principles helps design responsive systems. Grasping how processes and threads interact allows developers to build applications that perform smoothly and reliably, addressing potential pitfalls like deadlocks. Race conditions, live locks, and starvation is crucial. Proper synchronization and resource management are key to maintaining system stability. Effective IPC methods enhance communication and coordination. Choosing the right inter-process communication techniques ensures that concurrent tasks can share data and work together without conflict. By mastering concurrency, robust and scalable applications can be developed. This knowledge is essential for modern software development across desktops, servers, and real-time systems. Thank you for watching. Concurrency in operating systems involves executing multiple tasks efficiently. Understanding concurrency principles helps design responsive systems. Addressing potential pitfalls like deadlocks and race conditions is crucial. Effective IPC methods enhance communication and coordination. By mastering concurrency, robust and scalable applications can be developed.